Dear students, today we will start another application of Bernoulli's equation or Bernoulli's principle, that is Venturi meter. This Venturi meter is a device which is used to measure the velocity in a pipe. And to find the velocity in a pipe at a point, this Venturi meter is based on the principle of Bernoulli. First of all, you see its shape. You see there are three portions of this Venturi meter. One is the converging portion. It is converging to this throat. Second one is called throat, and third one is diverging portion. You see in these three portions, in the first portion, which is in the upstream direction, that is the flow is in this direction, the conical part is smaller in length, but the conical angle is bigger. In second part, there are constant cross sections. It is called throat. And again in third portion, it is a diverging portion in which this throat gradually goes to the original cross section like 1, and then it takes the shape of the pipe. So in this part, the conical part is longer, but its conical angle is smaller. Here the conical angle is bigger, but the conical part is smaller. So in this way it has three parts, and it is attached to a pipe. Here it will be attached to a pipe. Here it will be attached to a pipe. Now suppose we want to find the velocity at a point of a pipe, then this throat is brought to that point where we want to find the velocity. So in this way you see that it is a device to measure the velocity in a pipe. As I told you earlier, that this face, that means where the conical part is smaller, is put in the direction of flow, and this part is put in the downstream direction. Now the reason for this type of shape is that to prevent the loss of energy, first it has the converging section and then it diverges to the same type of cross section so that there is no loss of energy. So this is its characteristic. Then one more thing is that you see that here the cross section is diverging. So as we studied earlier, that in equation of continuity we have proved that if cross sectional area is small, velocity will be increased, and if cross sectional area is bigger, the velocity will be decreased. Here the cross sectional area is becoming smaller, and therefore the velocity at this point will be higher. And now Bernoulli's principle says that as the speed increases, the pressure will be decreased. So this is the point, this is the throat, or you can say that in the converging section, the velocity is increased and pressure is decreased, while in diverging section, the velocity is decreased and the pressure is increased. It is just due to the balance in the Bernoulli's equation. So we can say that velocity reaches its maximum value and pressure reaches to its minimum value in this throat. at 2. Gradually velocity decreases and pressure increases through the divergent part. So this type of flow through constricted, convergent and divergent passages was first demonstrated by Italian scientist Giovanni Battista Venturi in 1797 by an Italian scientist. Now we come to its application, that how we measure the velocity. For that, what we do, we attach a manometer from throat to this portion. This is a manometer, and in this manometer there is mercury, and the level of mercury due to the pressure of the fluid in the pipe will be like this. This is mercury with density say rho m or sigma, and this is having a fluid passing through it, and it is having a density rho. Now from 1 to 2, one stream is propagating. Now this fluid is also entering in this pipe, in this manometer, but I am drawing this as the reference level. Suppose this is the reference level, and also you consider a datum for calculation. So it is the datum. Up to this reference level, I suppose that from the datum this height be h0, similarly this is h0, let it be delta h, which you can see it is the difference between these two levels, this level and this level. This is delta h, and again this is having the same fluid which was in the pipe. आप इसको ऐसे कर सकते हो, and let this height, total height be z2 up to this point 2. Similarly for this point 1, let this height be z1. This height be z1 up to the datum. Now it has 3 parts. 1, convergent part, 2, throat, and 3, divergent part. Now we look at Bernoulli's equation. Along a stream from point 1 to point 2. For point 1, P1 by rho g, pressure energy, plus V1 square by 2g, kinetic energy, and its height Z1, its depth from the datum, that is Z1, giving you the potential energy, is equal to, it simply means that at point 1 I am assuming that P1 is the pressure and V1 is the velocity. At point 2, P2 is the pressure and V2 is the velocity. So for this, P2 by rho g plus V2 square by 2g plus Z2, because its height from the datum is Z2. Now solving it, we can find, or I say take it 1. Now we will use mass conservation equation. Suppose at this point I am taking the cross section as A1, and at this point I am taking the cross section as A2. So mass conservation equation says V1 A1 is equal to V2 A2, and we have to find velocity at point 2, so we need V2. So we will substitute V1 also in terms of V2, A2 upon A1 V2, and substitute in 1, and solving you will get now after solving you will get V2 is equal to square root of 2g upon 1 minus A2 square upon A1 square H1 star minus H2 star, where what is H1? H1 star is equal to P1 upon rho g plus Z1, and H2 star is equal to P2 upon rho g plus Z2. Now suppose Z1 is equal to Z2. It will happen if you take your it will happen when you will take your Venturi meter to be flat. Venturi meter is horizontal, because in that case level of point 1 and 2 will be same. So in that case your H1 star and H2 star will be changed, and H1 star will be P1 by rho g, and H2 star will be P2 by rho g. In this case you can also see that we will take this case later. Now I will take the balancing of pressure. From balance of pressure, we would try to find the values of these H1 star and H2 star. In this case we will discuss later. Now you again see at your diagram. In this diagram, this is your reference level. This is the reference level. So at this reference level, what is the value of pressure? This is the pressure, this P1, and the pressure due to this fluid. And how we count it? We count it P1 plus the density of the fluid. The density of the fluid is rho in this portion. So rho g into this height. What is this height? This is Z1 minus H0. You got it? See it again. We want to find the pressure at the reference level. At the reference level, whatever is the pressure here should be the pressure here. So both should be same. So first we count pressure here. This pressure will be this P1 जो हमने यहाँ पे consider किया है. This P1 and the pressure due to this fluid. तो क्या करते हैं हम fluid का pressure यहाँ पर जो pressure है उसे लेने के लिए density into gravity into this height ये लेते हैं. तो density कितनी है जो इस fluid जो यहाँ तक आया हुआ है that is rho. This is the density of the fluid which is flowing in the pipe. So rho g into this height. And this height is equal to Z1 minus H0. Similarly, at this point, we will count the pressure and that will be 1 P2. P2 because of this and then because of this fluid. तो जब हम इस fluid का लेंगे तो वो क्या लेंगे हम rho because this fluid has the density rho. Rho g into this height. What is this height? This is Z2 minus H0 minus delta H. And then we will take pressure due to this fluid. This fluid has the density rho m. So rho m into g into this height. So this height is delta H. So in this way we will write these expressions. From balance of pressure we have P1 plus rho g Z1 minus Z0. H0, sorry. It is H0 minus H0 is equal to P2 plus rho g Z2 minus H0 minus delta H plus rho m g delta H. Now solve it and get P1 upon rho g plus Z1 minus P2 upon rho g plus Z2 is equal to rho m minus rho delta H upon rho, or this is H1 star minus H2 star, you can see here, is equal to rho m minus rho upon rho delta H. You may take it as 2, this is 3, and this you may take 4. Now using this 4, equation 3 will become V2 square is equal to twice G A1 upon A1 square minus A2 square. This is also square. Rho m upon rho minus 1 delta H. Now, in case I want to find what is H1 minus H2 as I have assumed previously. This will be delta H rho m upon rho minus 1 delta H हो गया पहले. This is from I think this is from 4. Actually, what is it? This is the column head. So if you want to find what is the difference between the two levels, H1 minus H2, you just multiply that column head into rho m upon rho minus 1. This is the density of the mercury in the manometer. This is the density of the fluid minus 1. It will give you the answer of H1 minus H2. And then substituting this answer, you can get V2 square. And if I want to find the discharge, discharge means Q is equal to AV. AV means A2V2 in this case, क्योंकि हम क्या करते हैं डिस्चार्ज के लिए जो वेलोसिटी होती है उसको क्रॉस सेक्शनल एरिया से मल्टीप्लाई कर देते हैं. So in this case you multiply your V2 with A2, so it will be A2 A1 square root of 2G upon A1 square minus A2 square rho m minus upon delta H. Now again, as the actual discharge will be greater than actual theoretical discharge will be greater than actual discharge, as I told you earlier, because in theoretical discharge you have assumed your fluid to be non-viscous while there is some viscosity, so there will be the loss of energy due to friction, and therefore whatever you have calculated theoretically will be greater than Q actual. So the ratio of the two, Q actual upon Q theoretical, is called coefficient of discharge. Coefficient of discharge. And therefore to find Q actual, you multiply this coefficient of discharge by Q theoretical. You have to take in mind that if rho m is greater than rho in this 6 expression, then you have to write 6. 6 is okay. But if in any case rho 1 is greater than rho m, then in that case you have to reverse this expression. In 6, replace rho m by rho minus 1 by 1 minus rho m by rho, and other things will remain as such. Now the important thing which you have to remember is that angle of converging section should be between angle of converging section should be between 18 degree to 20 degree, and angle of diverging section should be between 6 degree to 7 degrees Celsius. Why we consider this type of angles? Because otherwise what will happen? The no slip condition will not be followed. It simply means when you go from the converging section to the diverging section, the fluid will leave the walls of the tube of the venturimeter. So in order to avoid the separation of fluid, these angles should be in this range. Okay. Because in that case, if it leave the surface of the diverging section, the loss of energy will be increased, and it is called a separation of fluid. So in order to avoid the separation of fluid, or in order to follow the no slip condition, the angle of converging section should be between 18 degree to 20 degree and angle of diverging section should be between 6 degree to 7 degree. And that's all for this application. Thank you.